Hi everyone, welcome to lecture 8.2 of our Möbius inversion miniseries. In 8.1, we look at strings of length n over an alphabet of C colors, and we used Möbius inversion to count primitive strings, the ones that are not made by repeating a shorter block. Today, we take the next step. Instead of keeping track of where the string starts, we bend the string into a circle and treat rotations as the same object. Those circular patterns are called necklaces. The new ingredient is symmetry. When we allow rotations, we're no longer just counting strings, we're counting orbits of strings under the rotation group. This leads to a beautiful formula for the number of necklaces n of n, where Euler's totient function phi appears naturally. To get the most out of this lecture, try to keep two pictures in your head. The first one is the linear picture from the 8.1. That is, you have a string of length n. You ask whether it is a shorter block of repeated several times. Now, in the second picture, now for this lecture, is a circular one. Imagine taking the same string of beads and connecting the ends to form a loop. Now, rotating the loop doesn't change the necklace. Anyway, try to watch for these parallels between line and circle while you go through the examples. So if you want to go back and view the previous 8.1 lecture.
Last time we counted linear strings by understanding their periods and using Möbius inversion. We began with simple strings laid out in a row, choosing each position independently from some alphabet of C symbols. Primitive meant that the pattern does not repeat earlier. You must traverse the entire length before it lines up again. Non-primitive strings came from repeating a shorter block, so their true period was a divisor of the length.
Now we want to see what changes when the ends meet, and we treat rotations of the same pattern as equivalent.
This move from lines to circles introduces rotational symmetry, and that symmetry will reshape our counting formulas. Let us turn the informal picture of a necklace into a concrete mathematical object. Picture beads placed at equal spacing around a circle, like a bracelet lying flat on a table. We fix an alphabet of C bead colors, and each position on the circle gets one of those colors. If spinning the whole necklace carries one coloring onto the other, we regard them as one and the same necklace.
So even if a flipped version looks the same in a mirror, we are not identifying that here, only actual rotations around the circle.
With that convention, we can now interpret counting necklaces as a problem about how a rotation acts on all possible bead strings. To count necklaces, it helps to see how rotations act on the set of all linear strings. There are n possible rotations, including the do-nothing rotation and the rotation that moves each bead one step, and so on. Take any arrangement of beads in a row, then imagine joining the ends so it becomes a circle. If you rotate by every possible amount, you see up to n different circular views of that same underlying string.
So each necklace is really an orbit, the entire collection of rotated copies of a single string.
Thinking of necklaces as orbits under the rotation group lets us bring in powerful symmetry counting tools. A key ingredient in symmetry counting is to understand which objects are fixed by each symmetry move. We spin the necklace so every bead moves k steps along the circle, wrapping around at the end. If you follow where a single position moves under repeated k-step rotations, you eventually return. All positions split into identical cycles of this kind. For the string to look identical after rotation, every position that moves around a cycle must carry the same color.
So only patterns whose true period is compatible with this cycle structure can survive that rotation unchanged.
This cycle viewpoint will lead to a clean formula for how many strings each rotation leaves fixed. We are now ready to write down a compact formula for the number of distinct necklaces. This formula says that the number of necklaces equals the average over all rotations of how many strings are fixed by each rotation. The cycles we discussed earlier depend only on n and k through their greatest common divisor, Once all positions in a cycle share one color, and cycles are independent, there are C choices per cycle.
So that exponent counts the cycles, and the base C counts the color choices for each cycle.
Burnside-style reasoning tells us that the number of orbits, our necklaces, is this average number of fixed strings. This expression already lets us compute necklace counts, but we can reveal more structure by rewriting it in terms of divisors of n. We can reorganize the rotation sum into a cleaner divisor sum that highlights Euler's totient function. Here, the sum runs over divisors d of n, phi of d counts certain rotations, and each contributes a power of c depending on n over d. Instead of summing over individual k, we bundle together all rotations that share the same greatest common divisor with n. Any greatest common divisor between n and k is by definition a divisor of n, so we naturally index by those divisors. Euler's totient function phi of d counts numbers that are relatively prime to d, which is exactly what appears when we classify rotations by their order.
So the totient factor says how many rotations of a given type exist, and the power of C says how many strings each of those fixes.
This divisor sum form mirrors many other arithmetic counting formulas and will be very convenient for computation. Next, we focus on primitive necklaces, whose patterns do not repeat before a full turn around the circle. From our previous work with linear strings, A of n counts primitive linear strings of length n via a Möbius inversion formula. Each primitive necklace corresponds to n linear primitive strings, one for each rotation. So we divide A of n by n to get m of n. A primitive necklace looks new at every rotation until you have gone all the way around once. If you cut the circle at different starting beads, you get n different linear strings that all represent the same necklace.
So A of n was already measuring how many full period strings we have before wrapping them into circles.
Sharing those strings into groups of size n under rotation gives us the primitive necklaces counted by m of n. This formula for m of n fits beautifully with the one for n of n, tying together Möbius, inversion, and rotational symmetry. Let us see the formulas in action on a small binary example where we can also visualize all necklaces. Plugging n equal to 4 and c equal to 2 into the divisor sum formula, we compute each totient value and see there are 6 binary necklaces of length 4. We focus on length 4, with beads colored either 0 or 1. Rather than listing all 16 strings, we lean on the formula involving divisors of 4 and totient values.
There are still 16 raw strings, but many fall into the same necklace once we group by rotation.
Drawing all binary necklaces of length 4 confirms that exactly 6 rotation classes appear, matching the formula. This small case reassures us that the divisor sum formula really matches the concrete orbit picture. Let us step back and connect the main ideas from necklaces to our broader themes. We redefined equality so that rotating the circle does not create a new object. Thinking of necklaces as orbits under the rotation group gave us a clean way to talk about symmetry.
By grouping rotations, we saw Euler's totient function appear naturally in the formula for n of n.
Möbius inversion controlled primitive linear strings, and dividing by n transferred that structure to primitive necklaces. Symmetry, orbits, and arithmetic functions like phi and mu will keep reappearing whenever we count structured objects up to equivalence. To finish, try one more computation and reflect on the ideas behind it. Use the totient-based expression for n of n and plug in n equal to 5 and c equal to 3.
Think about how rotational symmetry forced us to average over group actions and why totient and Möbius functions naturally appeared.
Carrying out this computation shows there are 51 distinct 5-bead necklaces using 3 colors counted up to rotation. If you can explain why that computation works and how symmetry drove the formula, you have captured the essence of this lecture.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.